All right, so this video is about power. And all that power is the rate at which force does work. It's the rate at which a force does work. And remember, work is how a force might add energy or take energy from a system. So remember, negative work is taking energy from the system. Positive work adds energy to the system. And you can also define work as the change in kinetic energy. And so positive work would increase the speed of an object, et cetera, et cetera. So we look at work, or excuse me, power, as the amount of energy that's being added to the system divided by how long it took that to happen. Okay? If we look at instantaneous power, you can look at for in very, very, very small time intervals what it would approach, and that would be how quickly energy is being added to or from the system and how long it takes for that to happen. So dW divided by dt. Okay? The units for power are the watt. I'm sure you have seen this before. And the watt is simply the units for work, which is a joule, and the SI units for time would be a second. So it's a joules per second. You can leave things as a watt or as a joules per second. So let's look at a couple more things about work. Okay. So we also have a formula for power, and this was really good for instantaneous power or for constant speed. Works out great. Okay, and that is for the dot product of force and velocity, which means that they do have to be in the same direction, remember, because it's the dot product. Very important there. Okay, and we get that because power is equal to work over how long it took to get there, how long it took you to add that energy to the system, which is force times displacement, okay, which would just be force times velocity. And these are both vectors, and remember it is, again, the dot product. Very useful formula. Okay. So we did this example in class, very simple one to start with. If a ski lift raises 100 passengers, averaging 660 newtons in weight, to a height of 150 meters in 60 seconds, what average power is required of the force making the lift? So we need to think of power is simply the work done by this force divided by how long it took to actually do that. And so in this case, we have to think of how much force needs to be exerted to overcome gravity. Okay, so I'm going to assume that this is at a constant rate. That way we know that the lifting rate, or the lifting force, will be the same as the gravitational force. Okay, so this is just mg, or in this case, it's going to be 660 newtons, and there's 100 of them. Okay, and so that lift force would be the same. So the work done by this lift force, if we divide that by the time it took to do that, the 60 seconds, that should be equal to the power. Okay, and so this should be the force done by this lift force, or the force of the lift, excuse me, times how long in terms of distance, and that the lift force was operating divided by how long it took to take it, or to do this in terms of time. So that would be 100 times 660, the lift force in newtons, and that took 150 meters divided by 60 seconds. So that ended up being 150,000 joules, or excuse me, joules per second. It often requires a lot of power to do any work. And so we could write this in kilowatts, 150 kilowatts. Okay. All right, now let's do this other simple problem. What is the power of the force required to move a 4,500 kilogram elevator cab with a load of 1,800 kilograms upward at a constant speed of 3.8 meters per second? So this constant speed here, let's think about this. We have two equations for power. It's going to be work over the change in time, and force times velocity, the dot product of that. Okay, and in this case, we have the velocity. We can simply find the force. Okay, the force would be, again, if you have the force of gravity and the force that's lifting the motor or lifting the elevator, whatever. This is going to be mg, and so this one should be mg as well. And so that's going to be 4,500. Oops. I don't know what I just did. So that's going to be, let's see, 1,800 plus 4,500 times 3.8. And don't forget about g's as well. And so that comes out to be 234,805.914 watts. Quite a lot of watts there. Okay, so that pretty much sums up power. We worked on the rest of the problems together in class, so there's nothing really that difficult about it. We're not introducing any crazy new concepts. It's just now is a rate of change of work.